Hello, hello. Okay, so today I am going to discuss this paper called Putting an End-to-End Gradient Isolated Learning of Representations, and this paper was published by Cindy Lowe. This paper was published by Cindy Lowe, Peter O'Connor, and Bastian S. Willing. Now, the reason I selected this paper is because it is a very fundamental paper and it is a alternative to backpropagation. So let's go through the abstract ones. So basically, what the authors are saying here is that they propose a novel deep learning method for local self-supervised representation learning that does not require labels nor end-to-end backpropagation. So basically, but exploits the natural order in data instead, inspired by the observation that biological neural networks appear to learn without backpropagating a global error signal. We split the deep neural network into a stack of gradient isolated modules. So basically, the key point is that in a standard backpropagation, what happens is that you have a sequence of layers. So let's say they are layer 1, layer 2, layer 3, and layer 4, and so on. So what will happen is that let's say you give it a input, which is input X. So what will happen is that first you will have to compute the activations in layer 1. It will pass through layer 2. It will pass to layer 3. It will reach layer 4. And then you will get some answer and you will compute the loss with respect to the answer. And then what you have to do is basically you have to do another pass through the network, which is like the backward pass which you carry out. So for example, here, the once you compute the loss, you have to actually come back and you have to compute the gradients, which you then use to update the parameters of layer 2, and then you update the parameters of layer 3. Similarly, you keep coming back, you update the parameters of layer 2, and then finally you update the parameters of layer 1. So this whole algorithm is basically called backpropagation, and this paper is saying that this algorithm is garbage and we need to actually come up with a better way to learn the representations in a neural network. So this is the core problem which they are solving, and let's have a look at their introduction now. So what they're saying is that uh, so end-to-end backpropagation has proven to be very successful, but this approach is very biologically implausible. The reason backpropagation is implausible is because you rely on a global loss, and then once you have to, if you rely on a global loss, you have to backpropagate the gradients, and you have to update every layer on the fly. And there is no evidence that such a backpropagation step happens in the brain. And another evidence like which these people are talking about in against backpropagation is that in the brain there are top-down connections in the brain and there does not appear to be a global objective. So here if you see the learning is driven entirely by this part which is this global loss. Without computing this global loss, you cannot update any of the layers, 1, layer 2, layer 3, layer 4. And what you actually, and in the brain, actually, nothing happens like that. Somehow, like when we see the data, all the layers of the brain are updated together in parallel. So this problem is what is like why some people are against backpropagation. And what this says is that instead the biological brain is highly modular and learns predominantly based on local information. So somehow like what happens is that let's say you have a brain and you have a set of neurons. So what happens is that let's say you are, so this neuron is only typically talking to the neurons which are in neighbor of it, right? And somehow the learning is happening and this neuron does not have a direct connection to another neuron. So let's say this neuron is having a path 1 and path 2. So this neuron is connected via path 1 to another neuron, and then it's connected to another neuron which is in path 2. So this neuron only talks to its neighbor, which is this one, and it does not talk to its second level neighbor, right? So it does not directly, so this neuron does not directly talk to this, right? And the only way it can talk to this is by passing a message from this neuron to this neuron, and then from this neuron to this neuron. So generally in the brain, what is happening is that when you are learning, your data, your input neuron, your neuron is only communicating with the neurons around it. And this type of learning is known as local learning. And in case of backpropagation, this is a problem because here what is happening is, suppose you have to update the layer 1. So your layer 4 actually has to compute the gradients, and all those gradients have to travel back to layer 1. So basically the layer 1 has to wait for the gradients from all the other layers to come back, and this is actually a very bad problem. Okay. So now let's move on to the other thing about what these authors are saying. So they are saying that supervised learning requires label data and requires label data, which is expensive to obtain. And that's true, right? Because in AI, we have to require a lot of data. And as a result, it is not possible to the majority of available data and suffers from a high risk of overfitting. Okay. So in normal AI, we basically have to learn and we have to actually require the labeling of the data, right? So you are given like input examples and you require like a lot of labeling, but that's actually not true in how like our brains work. So for some reason, like we can just look at the things around us and we don't need any labels, and that area is known as self-supervised learning. Okay. Now, the key point is that at the end, now another criticism of backpropagation, which is arised, is basically the part that at the same time, end-to-end backpropagation requires a substantial memory overhead as the entire computational graph, including all the parameters, activations, gradients, which need to be fit in a processor's working memory. Now, this is a very valid criticism of backpropagation because let's come back to this figure. So while you are doing backpropagation, what all do you have to store? So you will have to store the input, which is the input X. Similarly, you will have to, for every layer, so let's say there are 5 layers, you will have to store the weights of each layer, W1, W2, so on till W5. Similarly, then as your data is like moving through the network in a forward pass, you will have to actually compute the different activations. So like you will have W1X, and then you will have W2 W1X, and then you have W3 W2 W1X, which is a series of cascaded multiplications which you are actually forwarding through the network. And the fourth thing which you will have to which you will have to actually store is that when you are taking the loss, at that time you're taking the gradient of the loss with respect to the weights, right? So you're actually trying to store the gradients of all the layers, which is layer I to L. क्या हो गया? Okay, so then a further limitation of backpropagation is in this last layer objective, which is that the problem is perpetuated as end-to-end training does not allow for the exact weight of asynchronously optimizing individual layers. So basically, what this means is that there is a layer problem. There is a layer problem in backpropagation which is happening. So what it means is that let's say you have this data, okay, and you're sending a data as input X, and let we are only focusing on layer 1 right now. So let's say that you pass your data. So at time step 1, your data passes through layer 1, and then it passes through layer 2, layer 3, layer 4, layer 5. So till now, like 5 time steps have happened, and then you come back via back propagation. So you come back, which is time step 6, time step 7, time step 8, time step 9, and time step 10. So if you look at from the layers 1 perspective, what is happening is that the layer 1 is only computing the forward process during the step 1, and then it is getting updated during the step 10. So now the point is that for 9 seconds in between, which is the gap between this 10 minus 1 equal to 9, the layer 1 is not doing anything. It is just waiting for the layers which are after it to finish the compute. And this is actually a very bad lag which is happening in the system. But in our brain, like generally what happens is that all the layers are asynchronously updating with respect to each other, and they're able to adjust their weights. So this key issue is known as the locking issue in backpropagation. And unfortunately, like it has been a key problem in backpropagation. So what the authors say here is that the forward and backward the forward and backward locking of the network caused by backpropagation algorithm impedes the efficiency of hardware acceleration due to the lack of locality. Okay, so now in this paper, basically what the authors are trying to do is they're trying to come up with a new way, which they call as the greedy infomax training, that improves upon this problem. And the idea is that so what's the core idea of their paper? So the idea is that they will start from a given input X, and then they will try to learn a module one first, which is they will learn this module in some sort of unsupervised way. And once the learning of this module is completed, they will learn another module two on top of this. And then they will learn another module three on top of this. So they will try to greedily stack these models over one another. And then what happens is that each of these modules can be updated in isolation with respect to the other module. So each of these modules is actually what happens is that if you have any module here, let's say if you have any module here, so here what will happen is if you have this module, so this module will only, so at any moment of time, all of these modules can update together in parallel. So that's the first key innovation. So there is no locking issue. And the other thing is that this module only depends on computing the gradients using some local objective. So we will talk about that in more detail, but the key point is that once this module computes its own gradients, you can essentially update the weights of this block. And once the weights of this block are updated, you don't need to send any gradient back. So all of these modules can learn together in isolation with respect to each other, which is like a key advance. So let's talk about like what does this mean. So let me clear the board. Okay. So there are two messages which are important here. The first message is that you can train like different modules with respect to each other in parallel, and you can bypass this locking issue which was appearing in backpropagation. And the second question we are left is basically how does each of these block work? So how does each of these block function? So now let's look at the figure which the authors have shown so that it makes sense to us. So here what we have is that we have like these three blocks, module 1, module 2, module 3. And what's happening is that when you're inputting the data, the module 2 is looking at the data which comes at, and then it updates itself. And then it updates itself, but none of its gradients are sent back. So that is what this sign is showing, which is a stop gradient step. And similarly, the module 3 updates itself and none of its gradients are also sent back. Okay, so this is the key part. So first you will take and train like module 1, then you will train like module 2, then you will train a module 3 in this way. And the idea is that as you are like stacking these modules over top of one another, you are actually learning good representations. Okay, so now let us now talk about like what is the learning objective here. So the learning objective is pretty simple. Okay, uh, so let's say that you are trying to learn a particular module. Okay, so let's say that you are trying to learn a particular module which is like, so let's say this is a module M. Okay. And what happens is that this module is actually receiving the input over several time steps. So in your case, what it can actually mean is that, for example, you have images or if you have an audio signal. So let's say that you're given an audio signal which is up till time t. So you're given a audio signal which is given up till time t, and then so when you are like uttering a sentence, so for example, my name is Cat or my name is Rajat. Okay, so let me try to explain the objective of like, so if you have like different layers of the neural network and none of them is actually communicating with another and all of them are updating in parallel. So we need to invent a way in which like a particular layer could be updated. Okay. So basically like what the authors here are saying is that there is a concept called CPC. So CPC means contrastive predictive coding, and it was originally invented by Van Oord et al. In 2018, and it's a pretty powerful technique, and it's like nothing new. The idea is very simple. So let's say, for example, I am saying my name is Rajat. Okay, so you already know my name is Rajat. So as soon as I say my name is, so as soon as I finish uttering the word is, in future you know that Rajat will come, right? So when you are trying to process my name is, when you're trying to process the word is, you are trying to actually predict that in the future Rajat will come, and that's the whole idea. So, like whenever a neural network is looking at an input signal, it tries to predict some part of the future of the input signal, and it tries to like somehow know that what will come into the future. So this is like prediction into the future. So more formally, so let's say that you have an input signal. So let's say that you have like this input signal which is up to the time step k. Okay. So this is up to a time step t. Okay. So here it can mean my name is. Okay. So now what happens is that at time step t, it's is, and then it you have like a space for certain time. And then at let's say t k steps in the future, what you have is my name is Rajat. Okay. And then in future, like whatever will come is no longer relevant. So the idea is that if you are like trying to learn representations, what will happen is that when you're speaking something, you try to predict something in the future, which is like case steps later in the future. And then whatever happens after those case steps is no longer valid for you. So in this case, what happens is that if you look at the representations at these particular time steps, so basically what you want is that the representations at a particular time step t, and then the representations at the time step t plus k, which is so Rajat and is should be highly correlated together. And then whatever happens in the future, so if you pick any of these if you pick any of these other representations, they are like negatives. So if you so like you cannot predict like what, if you only see the word is, you cannot predict like what is gonna happen in much future, right? So you cannot predict like what's happened in a lot of other future. So all of these things are irrelevant to you. Okay. So how do you enforce this constraint in a network? So you are given like a certain set of, so you are given like a certain type of representation. So let's say that you are given a representation for is, which is a representation zt, and then you are given a representation at time t plus k, which is zt plus k. And similarly, you are given, let's say, a lot of other representations, which is like z J, ZJ1, and so on. So you're given like a lot of these other representations. So the whole idea is that the representation which is of the word is at that point should be closer to the representation in the future, which is the representation of Rajat, right? So in this case, so it's the ZT and ZT plus K should be close to each other, and whereas ZT and then all the other representations in the future, like they are no longer relevant because you're only looking at a span of t time step. So since it's not valid, that's why like you can get rid of all the future representations. So here like zt, and let's say maybe something which is like very infinite, right? So zj, so zt and zj are no longer relevant to each other. Okay. So if you can sample your representations in this way, you can actually divide your signal and you can enforce like certain representations to be close to each other and certain representations to be far away from each other. Then this thing is actually known as contrastive learning. Okay, so this is what like the authors are saying here. So what they are saying is that they have an input signal X, and what they are trying to do is they are trying to compute like the score. They're trying to compute the score between the input. So they're trying to compute the score between the representation at time t and the representation at time t plus k, right? And they want this score to be maximized. So they will maximize the numerator on the top, and then they can compute this score for all the other representation pairs. So in this case, my name is Rajat Modi. So is Rajat will be one, is Modi will be another, and then after whatever I speak, then whatever will come in the future, like you can multiply the representation of is with all the other words in the future, and those will be like the negatives for you. So you will take these representations and you will sum them up. And the idea is basically that the thing on the numerator should be high, and the thing on the numerator is basically a constant. So when you take this whole probability and then you take like a log likelihood of it and you are trying to minimize the negative of it, that's essentially minimizing the loss, right? So that's the whole idea here, that you find such sort of structures in the network and then you try to optimize them. So let's look at what the authors are doing here. So what they are saying is that they have a module M. So in this case, they have a module M, which is a particular layer of the neural net which they are trying to optimize. And let's say that the signal is given till time t, till time step t. Okay, so this is like the current word which you are considering. In my case, for example, my name is, so this is basically the ZMT, which is the representation at that current time step, and we want this representation to be close to the word which is like k steps into the future. So what we will do is that we will compute the representation of the word which is k times into the future, and we will also compute the representations for several words which are in the future after this, after the k time steps, which is like this uh, n minus 1 negative samples. So these future representations will act as negative, and some representation which is like k time step will act as a positive, and then you use the contrastive loss to bring them closer together, and then you bring and then you actually try to repel away these two away from each other. Okay, so this is like the whole idea, and this is how like you train each layer. So you have like a module 1 which is looking at which looks at the input signal, tries to choose a particular time step, tries to predict what's at the time step which is k times away from it, and all the other things in the future it pushes away from. And then once you train this module, then you go to the next, you freeze this module, and then you go to the next block, and then you train it in another way. So let's say you manage to train this whole system, then what will basically happen is something like this. So let's say that you want to train this, you train this whole system, and then what will happen is that uh, how will you build a neural network out of this? So let's say that you have a module 1, which you train through this contrastive approach, and then you have a module 2, which you train through this contrastive approach, and you keep on stacking these modules on top of each other. Okay, so let's say you build like n modules such as this, and then what will happen is that you will freeze this whole neural network and you will train a linear classifier on top of it. You will train a linear classifier on top of this, and all these blocks will be frozen. So there is no back propagation going on here. So you first learned representations by greedily stacking these learning blocks over one another, and then you trained a linear classifier on top of this. Okay. And that is how you are basically performing. That's how basically you are gonna perform a task like classification using this. Now you can imagine that you can also train like some blocks like this for segmentation, and then eventually you train a segmentation head on top of it. But the whole idea here is that you can train each of these modules without actually waiting for the gradients to come back. Okay. Now let's look at like what will be like some key advantages of such a approach. So what you can see is that let's say this neural network had 1,000 had 1,000 layers. Okay, so then technically what will happen is you can't put 1,000 layers on a single GPU, right? So what you can do is that you can first train layer one, then you can train layer two, then you can train layer three, and as let's say you reach layer 100, then you can cache all of these layers in memory, and you only need to you can cache all of these layers to the hard disk, and you can directly train a layer 101 in the computer RAM, in the GPU memory. So what this will help you is that you can do the learning process by only keeping some of the layers in the GPU memory at a particular time. And you cannot do that with a network like backpropagation, which requires like all the layers to be in the memory at the same time. And that was the key advance which led to which led to this paper being one of the most fundamental papers which I have seen over a long time. Okay, so let's look at the results. Uh, so I think this table was very good. So what it says is that let's say they are trying to basically train a ResNet 50 architecture for uh, for the classification task. So STL classification task, which is like they have like this speaker, and they're trying to actually understand how well it does. So here you see that if you use a standard CPC, which is contrastive predictive coding, which is the normal idea from 2018, it consumes a 7.7 gigs of memory. Okay, and that's because this network was trained through backpropagation. But if you look at their work, which is like greedily training all the modules together, and then so you are like having all the modules in memory, and you're training all of them together, then they consume 7.0. So 7.0 is still less than 7.7, because in this case, like when the layers are being updated, you are not actually propagating the gradients to other layers, right? So there is no propagation of gradients, but you're still computing the gradients. So the key point is that you are still storing the gradients, but since you're not propagating them, you're saving on the memory. Now, the other point is that let's say you only want to train the modules greedily. So let's say you train module one, then you train module two, then you train module three. So at a particular at a particular time, you're actually keeping like one of these blocks in memory, and that only consumes you 2.5 gigs. So what this means is that since they no longer need to keep all the 7 gigs in the memory, they can technically training each of these blocks consumes 2.5, and then they can keep training like thousands of such blocks by only consuming like 2.5 gigs of memory with respect to each other. And that's like a really good insight there. So that's the whole thing which they did. Okay. Now, let me show you some cool results which happen, which they are showing in their paper. So what they're saying is that uh, what they are comparing here is basically what happens if you train the module through backpropagation. What happens if you train the neural network through backpropagation versus what happens is like if you train it greedily. Okay, so let me just look at it once. Okay, so what you will see here is that so this first thing is known as iterative train, right? So what happens is that if they try to train like their neural network one layer at a time, so like first train one layer, then train second layer, then train third layer, what this is actually what this is actually leading to is that this training loss is actually falling down a lot. So they are overfitting, and then the overfitting is like a big issue versus actually training like all of these blocks simultaneously on top of one another. So that is like a trade-off which they have, which is like not that appreciable. Okay, so the key takeaway from here is that if you're trying to train like a neural network in such a way that you first train layer one, layer two, and then layer three, and then layer four. So if you keep like stacking the blocks, so when you're training layer four, you are no longer training the other blocks. So if you train like these blocks, lower blocks until convergence, and then you stack a block on the top, you will start running into an overfitting issue. And that's actually not a good thing. So what a good thing would be is to take all these four blocks and train them in parallel with respect to each other. So that's like the core takeaway which you get from their paper. And yeah, so I think that is the whole message of this thing. And actually, what happens is that they have some pretty interesting results if you look at the responses of the neurons. So, what they're showing here is the neurons which are actually present in, let's say, the module 1 in layer 1. These are the neurons in layer 2, and these are the neurons in layer 3. So, here, if you look at it very closely, so let me zoom in on it a little bit. So, if you look at it very closely, so you will see that the lower neuron is actually identifying some low level pattern. So here it's like identifying, let's say, the check related pattern. And then as you go to the above, to the neuron in the layer above, it's actually isolating like a higher level semantic concept, which in our case is like, for example, this part of the ship. So if you have multiple ships, it will activate itself only for a particular structure. So this is like a high level structure. And in as you keep going to the higher level, you will actually abstract away the information and you will end up with like a higher level semantic information. So what they're basically showing is that it is possible to learn these interesting representations even without backpropagation, and by just training the modules in this greedy way. Okay, so we have seen that, and now how does like their paper stack against? How does their paper stack against backpropagation? So the key point which so this CPC baseline is the original paper which was trained using backpropagation, and as you can see by using their method, their results are like almost 2% less than uh, almost 2% less than the state of the art, which is using like this sort of CPC loss. And then here it is like zero point 0.2 less than the core speaker on the core CPC baseline. Okay, so you can see that this is still creating like some problems, and that is actually not a good thing. So let me go over like all the baselines which are in their paper. So the supervised baseline means that they are just training a network end to end via back propagation, and then that is getting a 77.7 and a 98.9. So this is the standard where you optimize a neural network. Then they have a greedy supervised baseline where what they will do is that first they will train like their blocks. First they will train their module in a greedy way using the sort of objective which we have talked about, and then they will supervise it via the backpropagation step on the labels. So here like they get like 73.4 and 98.7. So they are still updating the layers in a supervised fashion. So in this baseline, basically the first step is that you go over the layers of a neural network, and then you are first updating them through this contrastive objective which I talked about, which is known as mutual information maximization. So you train each of these modules in separate to each other, and then once you have finished the training in phase 2, what will happen is that you take these representations you have learned, you reinitialize your network with that, you compute a loss, and then you backpropagate through the entire network on a supervised loss. So you are using the backpropagation in the second phase. In the first phase, you are only using the normal learning, which is like the local form of learning. Okay, so it is two steps, and that's why like you can see that this you can see that this is like so these results are like pretty high as compared to their own results. In CPC, what they do is that they first learn like only through the greedy way, so they perform like the phase 1, but they are not actually so they perform the phase 1, but they are not actually doing any sort of supervision on the during the back propagation step. Okay, and so this is their greedy Infomax, and it's cool to see that they are able to train like a network which is very near to the results in this case. Okay, yeah. So that was all which was important about this paper. And I think most of the other things, like you can read and try to find a good understanding. Uh, but let me go through like what are the key important takeaways from this. So in the conclusion, what the author said is that they demonstrate that deep neural networks do not necessarily require end-to-end backpropagation of a supervised loss, and rather what they are saying is that they can decouple the training, and each layer can be trained in isolation with respect to another layer based on a local objective, which in our case is basically the asynchronous distributed training. So you can predict, like, take case steps into the future, bring those representations closer, and all the other representations should be far apart. So by that sort of learning objective, you can learn each layer locally and you can optimize them in parallel. So now, what are like some key problems in their algorithm? So the first problem in their algorithm is that they still require negative samples. So the key point is that during the learning, when they're predicting like representations k step apart, all the representations in futures are acting as negatives, and it is not clear whether the brain relies on such negatives or not. So this is like a key constraint, which is the reliance of their network on negatives. And similarly, the other thing, which is the other problem in their network, is as follows. So let's say that they have to update the module. So let's say that they have to update the module 5. Okay, so first they will require module 1 to be trained, then module 2, then module 3, then module 4, and then module 5. So although like, so module 5 will only be trained after you have updated all the modules earlier. So it means that the module 5 is still suffering from the locking issue, okay? Which is that you have to update, or you have to train first this block, then this block, then this block, then this block, and then the representations you get are actually used to update the final block, okay? So this is like a locking issue and there is no way to go around it, and it still poses a fundamental bottleneck for their algorithm, okay? And what is like the key takeaway from this whole idea? So in the neural networks, there is a problem which is known as the credit assignment problem. So the credit assignment problem goes as this. So let's say you have a neural circuit and you have several layers which are like densely connected to each other, and there is a weight on each of them. Okay, so when you do a forward pass through an input, you're getting a particular answer. Let's say that answer is called R, and you want this answer to be correct. Okay, so the learning algorithm's job is that how much weight do you change to get the correct answer. So basically, for every iteration of the learning, you need to understand how much weight to be changed in order to get the correct answer. And the change in the weight, so if your weight goes from weight to weight plus delta, so this delta is known as the gradient of the weight, right? So you want to know how does the gradient change as you are performing learning, and what is a good way to get this gradient is the job of the learning algorithm. So sometimes what happens is that these learning algorithms, we are trying to understand like what is the real biological way in which the brain is getting these gradients, and it is not clear to us. So we try to come up with new type of learning algorithms which do this job. But the key point is that the idea is that there is like this credit assignment problem in the brain, which is like how does each neuron in the brain get the gradient required to solve a given learning problem. And we don't know the answer to that. So if we found an answer to that, we would solve this decade-long problem. And for now, it seems like the backpropagation is the best method we have. And it is the one which is responsible for creating all this problem, which is that keep stacking the layers and then keep getting the good performance. And this paper is hopefully a way which offers us way out of this problem. This paper was actually presented in NeurIPS as a oral back in 2021, if I'm not wrong. and it was presented by Cindy, and it was like a very influential paper, although like the citations are not that great, like only around 200 citations, but this does have the potential to represent the next advance, and I would urge you to go and look at this paper and also its video to understand what is actually happening. Okay, thanks, and let's move on to the next video later on.